Today we will go through a problem. So we are asked to show that for a Bernoulli trial with a probability of success P, we have to show that summation xi, the number of success in n trials, is a sufficient estimator of the parameter P. Okay, so let's see that x1, x2, etc. xn follows a Bernoulli distribution. Now the PDF is written like this: p raised to xi 1 minus p raised to xi, sorry, 1 minus xi. Okay, so that's it. Then now let's consider t, a variable t is equal to summation, sorry, a statistic t is equal to summation xi, since we have to find out that summation xi is a sufficient estimator of p. I'm just giving it as denoting it with a letter called t. Okay, now in order to find the sufficiency, first we have to find out the likelihood. So let's see what is the likelihood over here. L, how do you represent likelihood? Yeah, L of, it's a function, right? L of x1, x2, etc., xn, comma, your parameter. And this should be equal to L1, the statistic, that is something concerned with the summation xi and the parameter, multiplied by another function L2, x1, x2, etc., xn, which is independent of the parameter. Now if you are able to express this likelihood in this form, then we will be able to find out whether summation xi is a sufficient estimator of the parameter p. Okay, so for that, let's start the procedure. L of x1, x2, etc., xn, comma p is equal to, actually what is that, f of, what is the likelihood function, f of x1, you can also write this like this, no, f of x1, x2, etc., xn p, which is nothing but what, the product of the product of I is equal to 1 to n f of xi p. Now what is the product of why did I wrote this like product of 1 is equal, I is equal to 1 to n f of xi p? Yeah, you write this as f of x1p multiplied by f of x2p, okay, etc., f of xnp. Now instead of writing this whole story, is it okay to write like this, probability product of I is equal to 1 to n f of xi p, right? So I took this one, so this is equal to, again we have this whole story over here, just keep an eye on this. What is f of x1p? Now you have to expand. What is f of x1p? In this case it is p raised to x1 1 minus p raised to 1 minus x1 multiplied by p raised to x2 1 minus p raised to 1 minus x2 multiplied n times, you get p raised to nth term, p raised to xn 1 minus p raised to 1 minus xn. Okay, now what I'm going to do is I'm going to combine all this p raised to x1 plus x2 plus etc. plus xn, and then I'm going to combine all the 1 minus p 1 minus p raised to what will you get, 1 minus x1 plus 1 minus x2 plus etc. plus 1 minus xn, which is equal to p raised to summation xi, then 1 minus p raised to, here you have n ones, right? So n minus what, x1 plus x2 plus etc. xn. Okay, now how can you write this, p raised to summation xi, so this is equal to p raised to summation, just a moment, p raised to summation xi multiplied by p raised 1 minus p raised to n minus summation xi, see, n is over here, you took the summation of these values, so n minus summation, sorry, n minus summation xi, and yes, and I'm just giving it as multiplied by 1 over here. So here what I'm getting is this term is completely in terms of, you have your statistic over here, your parameter is over here, the random variable is over here. Okay, now this is multiplied by 1, which is independent of your parameter. So now you can write that L1 summation, instead of t you can write x summation xi p multiplied by L2 x1 x2 etc xn. Now where this thing is 1, therefore we say that summation xi is a sufficient estimator for p. Okay, next question, you have to show that x bar is a sufficient estimator of p when the sample size when the sample of size n is taken from a binomial population capital NP, where n is given. Okay, now let's see solution. x1 x2 etc xn are some random variables that are given. We know that x bar is equal to what? Summation xi divided by n. Then here in our case we are given that xi follows a binomial distribution with capital N and p, and n is known. Now you write the likelihood function as L of x1 x2 etc xn, which is equal to what? L1 of t comma p multiplied by L2 of x1 x2 etc xn. Okay, now you know that f of xi comma p, that is the density function of what a binomial distribution is given as ncxi p raised to xi 1 minus p raised to n minus xi. So therefore your likelihood function L of x1 x2 etc xn comma p is equal to actually what is it? Is equal to product of, this is not pi, this is product of I is equal to 1 to n f of xi p. Now what is this actually? F of x1p into f of x2p into etc multiplied by f of xnp. Now what will you do right now? Yes, you substitute the values. N C x1 p raised to x1 1 minus p raised to n minus x1, right, multiplied by n C x2 p raised to x2 1 minus p raised to n minus x2 multiplied by n times n C xn p raised to xn 1 minus p raised to n minus xn, which is equal to, what is the thing that you have to do right now? Yes, you have to combine certain things. So let's see, first I'm starting with p raised to, since it is much easier. Okay, p raised to x1 plus x2 plus etc xn 1 minus p raised to, what about this? There are n small n capital N's, right? So n's minus n minus x1 plus x2 plus etc plus xn, and then you have multiplied by ncx1 ncx2 etc ncxn. Okay, now this is equal to p raised to summation xi, okay, 1 minus p raised to n minus again summation xi multiplied by the combinations ncx1, ncx2, etc., ncxn, which is equal to, instead of summation xi, see our question is regarding what? You have to find out whether x bar is a sufficient estimator. Now in this here it is given as summation xi, so you should rewrite it as nx bar instead of summation xi. So that is why I have given a formula over here of x bar. So instead of summation xi, you can write nx bar multiplied by 1 minus p whole raised to nn minus nx bar multiplied by the other factors. Okay, now what is it that you have, that you are inferring from here? Now it is said that you can see clearly that this is L1 and this can be stated as L2. So we can say that this is equal to L of TP, where T is equal to x bar L1, okay, multiplied by L2 of x1, x2, etc., xn. Therefore we can say that x bar is a sufficient estimator of P. Okay, so let's move on to the next question. Now the next question is, you have to obtain the sufficient estimator of theta using a sample of size n, from the density function. The density function is given and it is what? F of x theta is equal to 1 by root 2 pi e raised to minus x square divided by 2 theta. Now solution: let x1, x2, etc., xn be the sample taken from the population. Now the likelihood function is given as L of x1, x2, etc., xn, comma theta, which is equal to, so what is your likelihood function? Usually you will write it as what? F of xi theta, right? Now this is equal to f of x1 theta, f of x2 theta, f of xn theta. So instead of this you can write this as what? 1 by root 2 pi theta e raised to minus x1 square divided by 2 theta multiplied by 1 by root 2 pi theta e raised to minus x2 square divided by 2 theta multiplied by 1 by root 2 pi theta e raised to minus xn square divided by 2 theta. Now what is the next thing that you have to do? You have to club all the values. So when you club it, what you get? 1 by root 2 pi theta the whole raised to n, because there are n times, e raised to minus 1 by 2 theta summation xi square, summation xi square. Hope this is justified. Then which is equal to you can write this as multiplied by 1. So this is your L1. You can express this as L1 and this as L2. Therefore you can say that summation xi square, you are asked to obtain an estimator, so you can say that summation xi square is a sufficient estimator for theta. Next we have to examine whether, next problem, the sample mean x bar is sufficient for estimating the parameter lambda in a Poisson distribution. So you are given a Poisson distribution and we are asked to find out whether the sample mean is sufficient for estimating the parameter lambda. So we know that the density function is equal to lambda raised to x e raised to minus lambda divided by x factorial, where x takes the values 0, 1, 2, etc. Now let x1, x2, etc. xn be the sample taken. Okay, now you write the likelihood function L of x1, x2, etc. xn lambda, which is equal to product of I is equal to 1 to n f of xi comma lambda. Now you have to represent, or you have to express this in terms of L1 and L2, right? So for that, this is equal to f of x1 lambda multiplied by f of x2 lambda, etc. f of xn lambda. This is equal to, what is f of x1 lambda? That is lambda raised to x1 e raised to minus lambda by x1 factorial multiplied by lambda raised to x2 e raised to minus lambda divided by x2 factorial multiplied by etc. multiplied by lambda raised to xn e raised to minus lambda divided by xn factorial. Right, so how will you merge this, or how will you consolidate this? Lambda raised to nx bar e raised to minus lambda, okay, that is one set, 1 divided by x1 factorial multiplied by x2 factorial, etc. xn factorial. So now this is of the form L1 and L2. Now you can say that by, so now this form of converting the likelihood function into the form of L1 and L2, you can say that this is also called as the factorization theorem. Factorization theorem. Okay, now therefore you can say that x bar is a sufficient estimator of lambda. Okay, I hope you have understood. Thank you.